Hello and welcome to the YouTube channel D Creations Resources. In this YouTube channel, you will find several exciting episodes pertaining to science. Now, come October, and one important event that takes place is the declaration of Nobel Prizes. It begins with the declaration of Nobel Prize for Medicine or Physiology. Then Nobel Prize for Physics is declared, followed by Nobel Prize for Chemistry. Now, in the two previous episodes on this YouTube channel, I have tried to explain the science in the prize-winning discoveries in simple terms. So, there was one episode devoted to Nobel Prize in Medicine, and there was another episode which was devoted to Nobel Prize in Physics. Now we have our third episode in the series, which is about the Nobel Prize for Chemistry. So the Royal Swedish Academy of Sciences awarded the Nobel Prize in Chemistry 2025 to Susumu Kitagawa, Richard Robson and Omar Yaghi. And they were awarded this for the development of metal organic frameworks. Susumu Kitagawa was born in Kyoto in 1951. He completed his PhD in 1979 from Kyoto University and currently is working as a professor at Kyoto University itself. Omar Yaghi was born in Amman, Jordan in 1965. He earned his PhD from University of Illinois Urbana-Champaign, USA in 1990, and he is currently a professor at the University of California, Berkeley, while Richard Robson was born in 1937 in Glasgow, United Kingdom, and currently he is affiliated to University of Melbourne, Australia. Now let us first understand the significance of the Nobel Prize winning discovery. So we know that climate change is driven largely by the buildup of carbon dioxide in the atmosphere. And a big challenge has been removing the carbon dioxide that's already up there. So this year's Nobel winning breakthrough offers a way to clean up the air while also creating valuable substances from what was once considered waste. So the greenhouse emissions can be reduced by trapping carbon dioxide using metal organic frameworks which have won the Nobel Prize. So now let us first understand what exactly is a MOF. So MOF or metal organic frameworks is a crystal made by joining two kinds of building blocks, and no prizes for guessing because it clearly says metal and organic. So there are metal ions which are the corners or nodes, and there are organic molecules which are the struts or linkers. And when we put these two together, then these parts form a repeating three-dimensional framework that contains lots of empty space or tiny pores and channels like rooms and hallways inside a house. Now, because most of the volume in a MOF is an empty space, 1 gram of MOF can have a surface area as large as a football field if you added up all the walls of those tiny rooms. So you can try to visualize, say, a Lego model where the pegs are metal pieces and the long bricks are organic linkers, and all these pieces are put together in a regular pattern, and we get a hollow lattice full of tiny cavities. So these cavities are very useful. They can be used for trapping gases or water molecules or other chemicals, etc. The idea was started by Richard Robson. He demonstrated how metal ions and multi-armed organic linkers can build large, roomy crystalline structures. And his early models were basically the blueprints for these molecular buildings, so as to say. Then came in Susumu Kitagawa, who showed that these frameworks could actually take in and release gases, and that some of these metal organic frameworks could flex or change shape when some guest molecules enter. And this is going to be useful for selective capture. If you want to capture only certain entity, then you need to know the repercussions, or you need to understand whether you have been able to trap that exact entity. Then Omar Yaghi developed very stable metal organic frameworks, and he gave chemists reliable ways to design MOFs with precise structures and functions. And so the earlier blueprints were now converted into practical usable materials. In order to understand how MOFs work, we should first imagine that we have chosen a metal ion like a corner piece and an organic molecule that can bind to the metal. So that is like a connecting rod. And then all this is mixed under controlled chemical conditions so that they link up and form a repeating three-dimensional. Now the resulting crystals will have many uniform pores, and the pore size can vary. Now molecules of a gas or a liquid will enter these pores and they will stick to the inner surfaces, or they will travel through the channels. In order to release or transform these trapped molecules, one would need to change the temperature, pressure, or chemistry, etc. There could be several such materials. So what is so special about MOFs? So these are customizable. Several different kinds of metals and linkers can be mixed and matched to design thousands of different MOFs. Each will have a specific pore size and a chemical character. Of course, as we spoke earlier, the internal surface area is very large, and this huge surface area means that these MOFs can hold a lot of guest molecules in a small bulk volume, and the inner walls of the pores can be given chemical groups that prefer certain molecules, so that MOFs can be made highly selective, or you can say that they can be tuned as per the requirement. There could be several applications, like as mentioned earlier, capturing of carbon dioxide, or there could be sensors where MOFs can detect chemicals. They can even be very good catalysts because they can hold reactants in their pores in the right orientation. This is going to speed up the chemical reaction, or it will enable greener processes. It can also capture tiny amounts of toxic chemicals. So basically they would be cleaning pollutants and acting like a filter, or they can pull water vapor from very dry air and release it when warm. This could be a very good way to collect drinking water in arid regions. So this is kind of water harvesting. Or they can be used for storing clean fuels. They can pack hydrogen or methane into small volumes, and hence useful for cleaner fuel storage. So you can actually think of MOFs like custom built houses for molecules. In a way, we are creating millions of tiny rooms and decorating their walls with chemical hooks so that we can trap, sort, store, or transform molecules in very unique ways. So MOFs are like a new engineering toolbox at the molecular scale, because we can design their internal spaces, and they have opened the door to tailor-made solutions for climate, for water, energy, medicine, pollution, etc. And we have already spoken about a lot of practical applications. So MOFs can be part of filters, fuel tanks, water harvesters, drug delivery systems, etc. And problems pertaining to stability, scale up, cost, etc. can be solved. So with this Nobel Prize, we understand that chemistry isn't just about mixing liquids in test tubes, right? How it is pictured all the time. It's basically the science of transformation. So here molecular science is linked to climate solutions, and chemistry is being used to address major global problems. So this 2025 Nobel Prize for Chemistry is intriguing because it is turning a clever molecular idea into a powerful platform which is going to help to solve real world problems.